Okay.
Well, the project, as it has been mentioned, is a big one, but its main topic is introducing a new type of quantum computing architecture that is named two-way quantum computing. And this topic is quite complex, so to say. So I will start with the original idea, which is also a different kind of architecture of quantum computing, which is one-way quantum computing. In a traditional gate-based approach, we are using gates on qubits, on single qubits. But in one-way quantum computing, we operate on so-called cluster states, which are highly entangled multi-qubit states. And only one qubit projective measurements are used on them to conduct computations. And one-way quantum computing, as the name suggests, is unidirectional, since when the entangled states are measured, the entanglement is irreversibly destroyed. In two-way quantum computing, a CPT symmetric approach is utilized, which means charge parity and time reversal. And especially the time reversal is important here. The main result that is a so-called, we can call it the new operation or a new way of doing state preparation is in the normal type of state preparation, we are controlling the initial state. And here we can utilize time reversal to change the direction of the state. And in that way, we will induce a projection on a neighboring qubit. And this will have implications for later projects, which I will discuss. But the physical implementation can be seen at the top image there, where electromagnetic impulses are applied to the state to prepare it, and traveling electrons are used here. So that's what's happening on the left. And the small equation with the arrow, which is v of t, changing to v of minus t, is reversing the time variable in those impulses. What can be used there is the EM impulses, which are used in quantum dot-based processors, for example. And then in the middle, we are applying a unitary evolution of the state. And on the right, we are utilizing the time symmetric approach. Since the process is reversed, and the way of reversing it is called postparation. That is a new term which will be used extensively in the following projects. So postparation is essentially the action of the projection due to the time reversed state preparation. So on the right, the process is reversed using the postparation, and the electromagnetic impulses will be time reversed, and they will enforce the final state. And with, well, so-called classic quantum computing, the gate-based approach, for example, only the initial state can be controlled. But in two-way quantum computing, we can apply the control to both sides of the system, the initial and the final. And that introduces a lot of potential computational power. And the aim of all those projects is to explore the way in which we can harness that power to improve existing quantum computing algorithms, architectures, and how we can implement it. And the first project is a project that I did with Betül. And in that project, we are exploring post-selection and its use with quantum computing and the potential improvements it can bring. With post-selection being a conditional rejection of some states during the computation. So, for example, we are rejecting all the states where the state is 0. And post selection can be quite directly implemented with using post-paration, since post-selection, for example, can be implemented using a projective measurement. And since we're projecting on a neighboring qubit using post-paration, the analogy is quite direct here. And since two-way quantum computing also employs bidirectionality and the projection, with the projection, we don't need to know the current state. There can be some improvements, existing improvements, which Betül will discuss.
Okay, let me, sorry. Can you hear me right now?
Yes.
Okay. So Alex talked about the first part, what we have done in our work. So I will continue, and we just right now examine, I'm sorry, my screen. Okay. Okay. And let's examine the physical viability of post-selection. Post-selection plays a crucial role in reducing errors in quantum measurements, particularly in weak measurements, actually. However, two-way quantum computing has the potential to further improve the accuracy of weak measurements by enforcing the final state. So how we can implement post-selection? One method is using the Hadamard test. The Hadamard test is a fundamental tool used in various quantum algorithms to measure expectation values. However, current Hadamard tests often require multiple repetitions to reach the desired sensitivity. With two-way quantum computing, this sensitivity could be improved by leveraging dynamic bidirectional control. Post-paration could allow quantum states to be more precisely controlled during both preparation and measurement, minimizing errors and reducing the need for repetition. This enhancement in sensitivity could lead to significant reduction in the computational resources required. Let's look at how this plays into quantum phase estimation. Quantum phase estimation is a crucial subroutine used in a large-scale quantum algorithms like Shor's algorithm. QPE often requires post-selection to manage errors during the phase estimation, leading to exponential scaling challenges. Integrating two-way quantum computation into QPE could help reduce the need for repetitive post-selection by enforcing the final state throughout the competition. This could enhance the accuracy and speed of the algorithm, making it more efficient for solving problems like factoring large numbers. Now, when we say factoring large numbers, let's talk about specifically about Shor's algorithm. One of the most important quantum algorithms, one of the challenges with Shor's algorithm is the rapid growth of the number of qubits needed as the number being factored. Qubit recycling, first introduced by Enrico Martin Lopez in his work Experimental Realization of Shor's Quantum Factoring Algorithm using qubit recycling, was developed to address this by allowing the same qubits to be reused multiple times. Here is where two-way quantum computing become even more available. Current qubit recycling methods require knowledge of the measurement outcome before a qubit can be reused. However, two-way quantum computing can overcome this limitation through post-paration, allowing qubits to be reset and reused without prior knowledge of the measurement outcome, making the recycling process more efficient and scalable. Furthermore, eigenvalue finding algorithms also stand to benefit from two-way quantum computing. These algorithms often require post-selection and encounter scaling issues due to repeated post-selection steps. By enforcing the final state using post-paration, two-way quantum computing could reduce the number of post-selection steps needed, allowing for more efficient and accurate eigenvalue estimations. This would make the algorithms more scalable and practical for use in complex quantum systems. In addition to eigenvalue finding, let's consider state reconstruction. State reconstruction is another quantum process where accuracy is crucial and post-selection is typically used to refine the results. However, achieving higher accuracy often requires multiple post-selection steps, which can be computationally expensive. With two-way quantum computing, post-operation could enforce the correct final state during the reconstruction process, reducing the number of post-selection steps required and improving the overall efficiency of state reconstruction. Let's now turn our attention to quantum machine learning algorithms. Many quantum machine learning algorithms rely on post-selection, such as variational quantum algorithms or quantum circuit-borne machines. These algorithms could benefit from two-way quantum computing's abilities to stabilize quantum states through post-operation. By enforcing both initial and final states, two-way quantum computing could reduce errors and improve the consistency of the learning process, leading to more efficient machine learning models. Now, we consider the application of two-way quantum computing to error correction. Post-selection is already used in methods such as accreditation protocol and probabilistic error correction, but these methods typically require many executions to correct time-dependent errors. With two-way quantum computing, post-operation could enforce the final state in just a single execution, reducing the number of operations needed to correct errors. This could also improve the reliability of quantum computations. For example, quantum surface codes, which rely on redundant qubits to correct errors, could benefit from two-way quantum computing by reducing the overall number of qubits needed while still achieving high accuracy in error correction. Lastly, let's explore the broader implications for complexity theory. Post-BQP, a complexity class of a problem solvable by a quantum computers using post-selection, could be further optimized with the introduction of two-way quantum computing. The features of two-way quantum computing, such as time reversal and post-operation, could simplify the solving of NP-complete problems by stabilizing the system throughout the computation. Additionally, this could give rise to a new complexity class called two-way bounded error quantum polynomial time. This class will build on post-BQP and extend it to solving even more complex problems by utilizing and stabilizing effects of post-operation. For more details, you can refer to Jarek's paper, three-set solver for two-way quantum computers. And to sum up, post-selection has been crucial tool in quantum algorithms. However, two-way quantum computing presents an exciting opportunity to optimize post-selection, improve accuracy, and reduce resource requirements across various quantum algorithms by providing a mechanism to enforce and stabilize quantum states during computation. And this is all, actually. Thank you for listening. And if you guys have any questions, we are listening.
Thank you very much. Any questions?
Is the Wolfram quantum computing framework free to use, or did you have like a subscription or something?
Yeah, the answer is on the chat, I think. Okay, any more questions? I think there will be a chance to ask more questions about this project after all the presentations regarding this project. So maybe because we skipped the project 16, is there anyone from this project with us right now? Okay, if not, then let's close this session and we will meet last time today at 2 p.m. to hear more about this two-way quantum computing project.
Just a second, Oscar, we still have one more, right? Or they are not presenting? Project 18?
Project 18. Oh, yeah, you're right. Sorry. Yes. Project 18. Is there anyone from this project with us? From Ioannis, so the mentor is Ioannis Theodonis, and the topic is simulating spin chains and exploring pointer state stability by optimizing parameters with control theory. Anyone from this project? Okay. So maybe I'll repeat the title. Project 17, meta-analysis of post-selection-based algorithms for practical approaches assuming conjugated state preparation. The mentors are Jarek, Duda, and Paweł Gora. Paweł joined us. Hello, Paweł. Now, who's going to present?
I am. Kindly make me co-host.
Okay.
Mah Noor here.
Okay. So you should be able to start.
Okay, so let me share my screen first. So can you guys see my screen?
Yes.
Okay, so before starting my own project, let me give you a summary of all the work we have done under the umbrella of 2V QC. Well, you guys have already listened to the amazing talk given by Betül and Alex on the optimization of post-selection in quantum algorithms. Now, I will be talking about no-cloning theorem in this architecture, and then Dave, Govind, Abdullah, Vaishnav, Jackson, and Kaushik will talk about Grover's algorithm under 2V QC umbrella. Abhishek worked on Vysakh problem, and Dominic and Vysakh will talk about the experimental verification of 2V QC. Last but not least, Jagit will talk about different attacks which we can implement on BB84 protocol or quantum key distribution with conjugate state preparation. So now let me start with my own project. So yeah. So I worked on no cloning theorem for two-way quantum computing. Why did I choose this project? Well, as you will see later, that this architecture of quantum computing is quite powerful. It increases the speed and accuracy of many quantum algorithms, famously Grover's algorithms. So there were many speculations that maybe this architecture can actually violate no cloning theorem. I spent a colossal amount of my internship trying to implement such an attack, which can actually break famously known as BB84 protocol. But after many futile attempts, I realized that it is no good. Like no cloning theorem still holds in the case of 2V QC. So let me proceed with this thing. So yeah, first of all, let's get an overview of what no cloning theorem is in case of one-way quantum computing. Well, we have in this case we have two quantum states. One is an unknown quantum state defined on the Hilbert space H subscript A, and the other one is known quantum state, or as we call it, target cloning state, which is defined on this Hilbert space. Now this theorem states that there can't be any unity operator U defined on this combination of Hilbert spaces such that it can clone an unknown quantum state to a known quantum state with the edge of a phase. So now coming towards the proof of no cloning theorem for one-way quantum computing. Well, first of all, let's assume that we have such a unity operator which can actually implement this operation, that it can clone an unknown quantum state to a known quantum state. Let us define our unknown quantum state. Here A and B are unknowns, but they follow Born rules, which means A mod square plus B mod square should be equal to 1. Now, such a unitary operator will act on a unknown quantum state and will clone an unknown quantum state to a known quantum state. Here, our known quantum state is actually initialized to be 0, right? This would be the expression that I will get, and by expanding it into the basis, I will get this thing. Now I can do the above formalism but with just a little bit modification. Before applying the cloning operation, let me expand this state phi like this, and then let me apply the cloning operation. Given that it is a universal cloner, which means that on whatever state it will act, it will produce an exact copy, or with some phase, a global phase, a copy of that state. So when it will act on 0, it should produce a copy of that state 0. When it will act on 1, it should produce a copy of that state 1. Now, if I compare both of these equations, what I will get, AB should be equal to 0, right? But AB can't be equal to 0, because in that case, either this thing will be equal to 0 or this thing will be equal to 0, which means that we can't actually clone a quantum state in case of one-way quantum computing. Expanding the same thing for the case of two-way quantum computing. Now, instead of 2 qubits, I'm dealing with 3 qubits. One for the unknown quantum state, the second one target cloning state, and the third one on which I will perform the operation of post selection. The theorem states that there can't be a unity operator defined on this combined Hilbert space such that it can actually produce an exact copy, or with some phase, the copy of an unknown quantum state on a non-quantum state. I will use the same formalism. So now the dimensions of both Hilbert spaces, the unknown quantum state one and the target cloning one, should be same, right? Because then I can actually produce an exact copy. I am again assuming that I have a unity operator which is actually capable of performing this operation. So I can expand an unknown quantum state in the basis of the in the terms of the basis of this Hilbert space H. Then I'm going to clone again this unknown quantum state in 2 ways. First, I performed the operation of cloning, and then I did the basis expansion thing. And in the second step, I first expanded the state in the basis, and then I performed the cloning thing. Now, if I again compare both of these equations, here inevitably we will have some values where u and v corresponds to different things, like it's 0, 1 or 1, 0, different states. So by comparing these two equations, we will easily get that this product should be equal to 0. So even in case of two-way quantum computing, we can't clone an unknown quantum state. So yeah, the theorem holds for the case of two-way quantum computing, and which actually means that we can't implement post selection attacks on BB84 protocol. This theorem is actually quite powerful, because it says that if we succeed in creating single photon sources, single photon detectors, and passive channels, then BB84 protocol will be unconditionally secure. And as a result of this internship, I also produced an arXiv. Here is the ID for that. And that's all from my side. Thank you so much for your time. So any questions?
Are there any questions? Okay, so maybe I'll ask a question. What are you planning to do next with this research?
So yeah, now we will be studying different implementations of quantum key distribution under 2VQC. Like we know that BB84 protocol is still unconditionally secure, but now we will study different other protocols which we know are not are secure under 1VQC. Will they still be secure under 2VQC?
Okay, thank you very much. So who's going to present next?
Yeah, hello, am I audible?
Yeah.
So hi, I'm Govind, and me and Dev are going to be presenting the next presentation.
Okay, please. You can present now.
Yeah, Dev, can you share the screen? Okay, so Dave has some network issues, so I'll just present my screen. Just give me a minute. Is my screen visible?
Yes.
So, hi everyone, I'm Govind, and our internship project here is focused on extending this Grover 2WQC quantum this approach to more number of qubits. So the motivation behind this project was basically to test out how does uh, 2WQC performs with increasing number of qubits and some imperfections, basically the noise in the environment. So we'll be starting off with just a basic circuit that is on the top left, as you can see, is of a Grover algorithm. So it involves basically these three steps here. First one is the superposition, then implementing the oracle, and diffusion, which takes place some root n times, which basically is the complexity in which the standard Grover algorithm operates. And as you also know that so here what we do in ToWQC problem statement here is that we generalize this oracle to some more number of qubits, where superposition here can be over n qubits, but the oracle implementation can also take place over some more number of qubits. And basically we tested it out for 10 qubits here, and the significant difference that you can see in this 1WQC Grover and 2WQC Grover is this CX operation and then product with the Browon in the end. So these are just the equations that can mathematically let you know about how does 1WQC Grover and the 2WQC Grover work. Then here are some snippets from the quantum circuits that we tested out. As you can see, let's go to the quantum circuits first. So the circuits here can the circuit on the bottom left corner is like a 5-qubit circuit where MCZ operation is implemented, followed by a diffusion operation. Whereas the circuit here is a 5-qubit gives solution to a 5-qubit Grover, but more than 5 qubits, or basically more qubits are used to construct the oracle. And the thing to note here is that there is a CZ operation that is used on the qubits in 1WQC Grover. Whereas you can see that in the 2WQC Grover, you just need to have this one extra CZ operation that replaces your CX operation that replaces your CZ operation in both the cases. And after this, you don't need to typically follow the approach that you use in standard Grover, which is the diffusion, which increases the time complexity. And 2WQC actually reduces the time complexity from those root n iterations of the diffusion to just order of 1. Then to simulate this Grover's algorithm for real world scenarios, we used penny lane to see how does noise act on the circuit that we created. So these are like the noise models that we use for simulating a circuit, which is bit flip, phase damping, and a depolarizing channel. And yeah, that's from my side, and I think Dave will carry forward with the remaining presentation. So thank you.
Yeah. So I'll be sharing the screen.
Should I
And
keep presenting? Okay. Yeah.
I have requested the permission.
Yeah, can you try sharing now? I think you are first.
Yeah, one second. Okay. So is the screen visible?
Yes.
Yeah, okay. So the first thing which I like to present is Oracle design and circuit design, which was proposed by Gregor Zaluza. His reference can be found above, and it was for marking the two target solution for a valid 2x2 Sudoku. So in a valid 2x2 Sudoku, like this one, the B0 should not be equal to B1 and B2, and B3 should not be equal to B2 and B1. This can also be represented by the XOR operations like this. So B0 XOR B1 equals to 1 and so on. So the target state comes out to be 1, 0, 0, 1 and 0, 1, 1, 0. So this circuit is for the classical Oracle, in which you can see the Oracle and the diffusion operator for the classical 1WQC, and this is for the 2WQC version with a Bra1 operator. And these are the noise curves. Uh, so we use the depolarizing noise channel for this, and as you can see, the 2WQC versions is more resistive towards the noise than the normal 1WQC version. And in this case, we induce a certain amount of noise in the Bra1 operator using the Kronecker product, and the noise value was somewhere around 0.2. And as you can see, the success probability went from 1 to somewhere around 0.7. But the thing to note here is that the noise was pretty high, and anything below 0.2 was not showing a significant change in the success probability of our circuit. Moving forward, so these are the noise resilience comparison for a depolarizing model, and the first one is for the 2WQC circuits for 2 qubits up till 6 qubits. And as you can see, as the number of qubits increases and number of gated operation increases, the noise in the circuit also increase. But again, it's worth mentioning that this is better noise resilience than compared to the 1WQC version. And this is for the 5 qubit circuit. We are just showing for the 5 qubit circuit, but we have also calculated for 6 qubits also. So for marking 1111 state, this is for the circuit with 3 extra ancillary qubits. And as you can see, the 2WQC version, the blue line is better when compared to the normal classical Grover's operator. And this is for the one with the rightmost one is for the multi-control Z gate without any ancillary qubit, and it performs better noise resilience than the one with 3 ancillary qubits because of less number of gated operations. And this one formula, with success rate of post-selection 1WQC is equals to success rate of 2WQC multiplied by success rate of post-selection, was proposed by Jarek in his paper. It can be found in the reference in the next slide. So in this, the post-selected 1WQC is somewhere around 2 to the power minus m, in which m is equals to 3 in our case, with the 3 extra ancillary qubits in the post-selected qubits in our 5 qubit circuit. So it comes out to be 1 by 8, and that is equals to 0.125. And the success rate of the success rate of 2WQC was calculated around 1. Uh, and the success rate of post-selection from our approach came out to be 0.126. So this validated the formula above. So yeah, that's it. Moving forward, for the conclusion, we can say that the 2WQC version of Grover's algorithm outperforms the 1WQC in terms of noise resistance. It's quite evident by looking at the plots. And the 2WQC Grover's operator also eliminates the need of diffusion operator and the amplitude amplification, which results in decreasing the time complexity from order of root n to order of 1. In the end, we also verified the formula for success rate of post-selected 1WQC, and these are the references. So yeah, so that was what we did. Thank you.
Thank you. Any
Any
questions?
questions for us?
Yeah, to both presentations actually, because we didn't ask.
Yeah, I had a few questions.
Yeah.
Yeah, so like in the first part, you presented that in the 2WQC groover, there is a need for extra qubits, but that's because just for like decomposing the multi-control Z or X, right? That is true for both 1WQC and 2WQC.
Yeah. So, Dave, can you share the screen? I'll just explain.
Yeah, 1 second.
You mean this one,
Yeah.
right? The oracle. Yeah. So basically, this oracle, if you implement this CX operation, it's a oracle where you have Hadamard superimposing just 5 qubits, and you have 3 remaining ancilla qubits, right? And whereas the oracle utilizes the remaining 3 ancilla qubits in its composition, and this oracle will be followed by a certain iteration of diffusion for 1WQC approach to work. But whereas this in this 2WQC, what happens is basically you just have to run the oracle once, and then take a CX and take a Brown like product with a Brown operation to get your desired solution value.
Yeah, but like then 2WQC doesn't require extra qubits, right? If you are also decomposing the multi-controlled C0 or CX in the diffusion part of 1WQC, the number of qubit requirements is kind of same.
Yeah, but this was just to make a comparison between what happens with increasing number of qubits and less number of qubits. So
Okay,
that
yeah.
was the main focus. Yeah.
And yeah, one more question. So when you're doing the simulation, is it also possible to and what's the effects of, let's say, measurement noise on post-selection or the BRA1 part? So are you assuming that there's no measurement noise, only gate noises?
No, so we do introduce a noise in this BRA1. So this BRA1 will basically be defined ideally by 0, 1, right? But we introduce certain epsilon and 1 minus epsilon value to introduce some imperfections in that operation. So if you plot like a histogram for 0 and 1 and not epsilon and 1 minus epsilon, you'll just be getting just 1 spikes or 2 spikes based on your number of solutions, and the other states will just go down to 0. Whereas if you introduce some epsilon error in that, you'll sort of get some remaining values of that as well. But you'll also observe a spike, which is not exactly like a 1 probability, or but you also find some other states that will be marked because of the imperfection there.
Okay. Thank you.
Are there any other questions? Okay, you can move on.
Yep.
So
Thank you.
Thank you very much. And now, who is our next speaker?
Yep, I'm here. All right. So basically, we have 2 different parts of the presentation. One was right here, which is more of just a summary page, and one which is like our main presentation. So I'll be referencing kind of them both. This one is more of a skimming, and this one more is results based. Okay. So our thing was exploring post-selection methods for Grother's algorithm, performing information theoretic analysis, complexity, and circuit efficiency and hardware scaling using the IBM quantum hardware by Vaishnav, Abdullah, Jackson, and Kaushik. Just an introduction to post-selection. It's a process to discard all computational paths that don't lead to desired state. It's a classical process that can't be physically realized, but we can simulate it. And these are basically just the basic steps for the post-selection. In this method, post-selection just assumes the role of both the oracle and diffuser, and the quantum circuit creates the superposition of every state possible. It is one of the most just basic, I guess, examples of post-selection that we could have used. Here's the matrix, the projection matrix we used by doing a 1, 0, 0. 1.0 projection matrix onto that. This operates on the quantum states, and we can get a matrix from its diagonal pretty much, and then we normalize it to make sure all the probabilities will return to 1. And here's just an example of that results where we tested a 3-qubit state, and we all got around 1/8 probability for all of them, but after post-selection, it was 100% on 0, 1, 0 qubits. And for this, this is the Oracle post-processing, where it makes states like take over the role of the diffuser, and the ancilla qubit is entangled with the marked state. This is just a explanation of the quantum circuit we used. And this is what the post-selection and the code and the post-selection does, and what our code implementation used for our thing. And this is just the results. This is a 4-qubit state this time for the one-way quantum computing rovers, and it shows that while some states do not get any percentage of the distribution, some states get all, as we showed previously. This one again, and this is our circuit for the quantum algorithm. And now on to the information analysis part. To start off, we went with a more classical term of entropy, Shannon entropy, and we calculated that between the two-way quantum computer Sudoku Grover's algorithm and the normal Grover's algorithm that was shown in the paper done by Gabe Celesta. We also tested von Neumann entropy given by this formula, and tested it between many different, again, between the regular quantum computing algorithm and the two-way quantum computing one. We also tested for fidelity, which is how similar two quantum states are, and we test them between their initial state and their final state just to test how similar they were in between the start and the end. And then we also tested for mutual information, which it quantified the amount of information that one system can do on another system between a joint entropy being subtracted by the two individual entropies. This is just our results from that. Here's a group of charts that we did. Just a group of charts that showed every measure. You can scroll down, you can see its individual qubits and subsystems that show the different types of fidelity, mutual information, Shannon entropy right there, or just von Neumann entropy in general. And then we tested it against noise strength. Yeah, just to see what our results would be. This showed here. This was the comparison between the two-way quantum computing and the regular one. We tested between various noise strength. And this is just a summary of the results we got up there. Showed the max success probability for the two-way quantum computing was much higher than just the regular Grovers, so we determined that it performs much better in terms of that accuracy as compared to the other two. And here's just a table that kind of enforces that. Another thing we did was we evaluated the efficiency. We compared the execution times on the standard and the two-way using default qubit and default mixed. And here's just the results of that. Here are more results. And yeah, as you can see, the default mix takes more time on both two-way and standard, but the two-way quantum computer in general takes less time to execute than the standard, which shows an advantage possibly of two-way quantum computing. And then here's just how we simulated and hardware scaled our algorithm. This is just a explanation of what we used to set up the algorithm. For our results, we tested between default qubit mixed, qubit autograd, qubit jacks, and well, the default qubits were 0 seconds. Default mixed and qubit jacks had a few seconds that were tacked on to it. And here's just a summary of the simulator results. They all came out pretty much the same with this is the post-selection, and everything was around 1/8 of the 8 states that we tested on. So then we tested it on the hardware in IBM Kyoto. Here's just our circuit specifications. We tested it again to see the probability distribution, and as it showed from our previous ones, the result on the hardware was the same as our theoretical one, where after post-selection it'd be 0, 1, 0 at a full probability of 1. And this is the one for the two-way quantum computing one. Here's our circuit specifications and gate types, gate sizes again. This was on a simulator, for Qiskit IBM Q. The Q time was around 4,700 seconds, and the running time was 48 seconds. We had 1 execution and 1 batch. Use the default qubit and 5 wires for the two-way quantum, because that's how it goes. We found the circuit depth was 17, and the maximum number of gates we could use was 32. Here's just a more in-depth version of that, which each of the gates were, and again, the default qubit. For two-way quantum computing, we found that we had a circuit depth of 9, and the maximum number of gates was 12. 5 wires again. And here's just a more detailed version of that. And in order to visualize the standard Grover circuit, we used the draw MPL function, which is able to show us what the circuit would look like in terms of a schematic. And these are the different simulators we use between just default ones and the Qiskit ones. And from our study, we can determine that two-way quantum computing Grover has this lower circuit depth than the standard one. It is more noise resilient, and post-selection methods can reduce run times on the hardware. Yeah, and here is this slide pretty much. Okay, I think that's all. Is there any questions?
Thank you. Any questions? Yeah, maybe I have a question about this noise resilience. If you could elaborate a bit on that.
Yeah, I'll share screen again. No, what was your question?
In what sense it is more noise resilient?
I'll pass it along to Abdullah, I believe, or Vaishnav, whoever worked on the noise resilience.
Okay, so this is like the same nose model as before.
Well, okay. I'm sorry. This is a group, and I wasn't the one that worked exactly on noise strength. But I think I can try to explain it. Just from these graphs, it shows the fidelity. So the fidelity compares the initial states to the final states, for example, and it shows how similar they are, and if they're affected by any noise for some reason, the fidelity would go down, but the fidelity of the two-way quantum computer stays strong throughout the noise strength. It's like you can kind of see in most of these graphs how from Grover, one-way quantum computing, whether it's one repetition or algorithm or the two repetition.
Sure.
The two-way quantum computer always makes sure to stay relatively high as compared, or it doesn't taper off as much So it just shows more resilience as compared to the regular one, because as you can see here, with just a little bit of noise in most of these cases, the values of these the value of these drastically change as compared to the regular two-way quantum computer.
Okay, thank you. Who's presenting next? Do you have any more presentations? Or was it the last one? Jarek, Paweł, do you have any more presentations?
So yes, in theory there should be three more. Could one of you? So if Abhishek has problem, maybe the next person could. Is there Abhishek?
Yeah.
Yeah.
Yes.
Okay.
So could start? Yes.
Yeah. Am I audible?
Yeah, I'll make you a co-host. Okay.
I will share my screen. Greetings of the day, everyone. I hope you are doing well.
Yeah, now we see Zoom, your Zoom window.
So I am Abhishek. I have been working on the satisfiability Boolean problem for this QIntern program, and I'll be explaining what I have worked so far. So my topic is reset using two-way quantum computer. It's enhanced imperfection models, QR gate optimization, and the depth simulation. So reset is a type of Boolean satisfiability problem where the goal is to determine if there is an assignment of two values to variables that makes a Boolean formula true. And there are many applications of this problem in classical and quantum computing. The way we understand this problem and handle is crucial for further advancement of our quantum computing capabilities, particularly in error correction and optimization. So the study which we had focuses on the error reduction, the optimization of gates for minimal error propagation, and the simulation to understand the impact of the circuit on its performance. So the key findings and techniques we had, the imperfection modeling. In this, we have to consider the decoherence and volume value cloning imperfections significantly, which are impacting our quantum circuit performance. And we have to redefine the circuit to predict and mitigate errors and improve the satisfiability problem efficiently. After that, we have to consider the gate optimization part. We have to decompose the gates in further basic gates like CNOT and Popoli to minimize the propagation. And furthermore, we can include the ancillary qubits and fault tolerant gates to further help us in reduce the errors. And as well, we have large base simulation. The deep circuits are more prone to errors because of if there is some issue in one gate or basic gate, that will propagate to other gates as well. So for that, we use circuit codes which are very essential. And the simulation will guide us to maintain the algorithmic performance at greater depth. So the paper which we already had published by our prof, Jarek. This is the paper. It's on arXiv, but still there are some future works which we will be working on. This is the basic preset setting. As you can see in the diagram, we have four n variables and m clauses to prepare the ensemble of 2n inputs, and we have to calculate COR gates and with NOT gates. we have to measure and get the results as as the expectation, but we have to minimize the errors and keep the circuit in serial and parallel configurations like this. So the error, the imperfection model helps us in reducing the error furthermore, and it settings to exponential for ON copies, it settings exponentially. Next, I will have a quick overview of this topic. So my colleagues already discussed about what the quantum computing is and the basic differences between one-way quantum computer and two-way quantum computer. Now the main topic, which the CPT symmetry is the very relevant term in quantum computing, and this is the backbone of behind two-way quantum computing. This is the charge conjugation parity time, and it holds for all the physical phenomena, like it's already been discussed by other scientists as well. And if there is violation, it implies the Lorentz invariance violation as well. So further, we'll continue with the pre and post paration. Pre-state preparation is the initial state, and the post paration is like in the reverse state. Like we should allow bra 0 and get not against CP2. So before getting this configuration of two-way quantum computer, we basically include the super dagger term in Wolfram quantum framework. This is the main reason which get output for two-way quantum computing. And the basic philosophy for CPT is the hydrodynamics and electrodynamics, like the push and pull, or the pressure, low pressure, and high pressure. All these terms are mm, correlated. Like the P space complexity classes, further we can discuss the reset problem and its relevance. The P is the polynomial time algorithm, and NP is not deterministic algorithm polynomial, and it depends on satisfying inputs. The factorization problem is the basic one, and for NP complete, it is the most difficult NP problem between problems, and in this we have this PSAT, and it is solvable. P space is solvable in polynomial space, and P space complete is, for example, reset for all universal quantifier games and or puzzles. So this is the setup which we have already discussed, the basic reset setting. It's been published on arXiv. So in imperfection model and the equalizer gate, uh, I will explain again the data optimization of COR gates in the two gates, decoherence and imperfection, and future works. This is the summary. I will recap the 2Ks around entry problems, how the 2K, 2WQC will be helpful in solving entry problems like we said. The future prospects will have a look. This is the reference which I have been using. Just give me a second. Yeah, this is the work which I have already put my time and effort. The imperfection model, I basically introduced what imperfection model is. In this decoherence, gate errors, any kind of noise significantly impact the performance of the algorithm. These terms under this. The decoherence is the loss of quantum coherence due to interaction with environment, and this can be rectified using Limbad equations like bit flip, phase flip, or depolarizing noise. Further, we have value cloning information. In this, we have to consider fidelity loss and perturbation analysis. Then we have error mitigation strategies in this reductive encoding and noise reducing cloning techniques will be explored. Furthermore, we have compound error model. In this error propagation, this is basically due to deterrence, and those are the main which impact our circuit. Coherence time limit. This is the effect. Circuits are designed to narrow down the time to avoid excessive error accumulation. Impact on FreeSat, this impacts the error threshold, and further we have to optimize the circuit design to reduce any such type of determinantal errors. C gate and its importance here. Control OR gate is the crucial critical multi-qubit gate in two-way quantum computers, and for solving research problems, we have to implement these gates. Further, we can decompose C OR gate into basic gates. The step-by-step decomposition can be done using Toffoli gates, control NOT gate, and further, this Toffoli gate can itself be decomposed into C0, Hermit, and phase gates. Furthermore, we have to use C0 and single qubit gates. This is the which flips the target qubit based on the control qubits. And killer qubits can be used to store the temporary state and for primary qubits to retain its integrity. This is the for the reduction of complexity of interaction between qubits. For example, if we are using a 4 qubits COR gate, we can further decompose it into 2 control qubits and 1 target qubit. So 2 CNOTs, 2 control qubits, CNOTs, and 1 control and killer qubit, and the remaining qubit. Error propagation and mitigation. In this, we have to minimize the errors. So fault tolerant gate construction has to be considered, and killer assisted error correction, as well as circuit optimization. Practical implementation. We have to
excuse me. Yeah, we are technically the time is up because it was supposed to be 40 minutes for presentations, and there are still 2 presentations. So if you could wrap up.
I will not take much time. This is the last. I will just wrap it as fast. So further, we have to simulate the largest circuits, the impact which we have in these circuits, because of decoherence and gate errors. Entanglement, circuit complexity, these are the basic factors which impact our circuit, and the simulation part basically depends on the circuit depth and the gate fidelity. So for error correction, we can use these techniques: surface code or concatenated codes or lightweight error detection. The impact on performance will be rectified using these trade-offs. Simulation results can be compared and for the further improvement in performance. Success probability matrix, these are the terms which will come. This is the conclusion. I will just wrap it as fast. For in future research will include refining the techniques and ensuring they are robust and for practical and large scale quantum applications. And further, we will explore advanced error correction code tailored to a specific quantum algorithm for maximizing for computational power. I would like to acknowledge and thank my professor, Prof. Duda and Prof. Gora for giving me this wonderful opportunity for presenting this paper and being in this organization.
Okay, thank you very much. It's nice that you managed to write a paper based on the work.
Okay.
I think we will we'll skip the questions for now. Maybe we'll ask some questions like the general questions to the whole project. Yeah.
Sure. Thank you for your time. It's my pleasure.
And now, yeah, who's going to present next? 2 more, right? 2 more presentations.
I'll be presenting next.
Yes. Okay. Okay, please go ahead.
Great. Well, hello everyone. I'm Dominic, along with my colleague Vysakh, and we'll be discussing the preparations we've made for two experimental tests meant to verify the principles of two-way quantum computing. I'll be describing one of the experimental verification methods proposed for two-way quantum computing involving stimulated emission absorption for external targets. So the diagram seen here illustrates the proposed experiment to test what is constructed as the hypothesis CPT or HCPT against the hypothesis absorption only or HAO. So the system here primarily contains a ring laser, which provides unidirectional photon trajectories along with two external targets in our system. On the right, we have a standard target prepared in state 1, and on the left, we have the CPT state preparation target represented as 0, state 0 in the CPT perspective. And the blue arrows represent the photon path traveling from the ring laser through the optical isolator to the right target. And the purple arrows show the CPT symmetric perspective, where photons appear to travel in the reverse direction. On the right, we have positive radiation pressure associated with standard state preparation. And on the left, we have negative radiation pressure linked to CPT. The bottom of the diagram displays Einstein's equations for stimulated emission and absorption, which are central to the experiment. The questions that we're primarily addressing is which of these two equations acts on our two external targets? And this is really the fundamental distinction between HCPT and HAO. I should also mention that the setup also includes a detour, and this modification could potentially transform our external targets into internal ones, which may affect which equations apply. So some direct tests we can use for determining whether HCPT or HAO is the correct hypothesis involve a ring laser and a standard laser. So when using a ring laser, we first excite a target behind a ring laser in which our excited state N2 is greater than 0. We then open the shutter and monitor the population, and if we find an increased de-excitation rate from N2, we'll see that HCPT is supported, and no change would support HAO. When testing using a standard laser, we start by using a laser without an optical isolator. For HCPT, we'd find N2 to be less than or equal to N1, which would mean a population bound. And in the case of HAO, we would possibly see N2 to be greater than N1, which would indicate a population inversion. Just to observe some population dynamics, we find that in the standard laser setup that N2 and N1 converge to the same value if HCPT is correct. We don't really see this with HAO. And additionally, if N2 decreases when N2 is greater than N1, then we would have confirmed HCPT. So the procedure for carrying out these tests begin with preparing and calibrating our system. We also calibrate our population monitoring system and test the shutter's timing precision. And then we excite our external target via a secondary laser. But before introducing our ring laser, we establish a baseline in which we record the natural decay rate of our excited target without any ring laser exposure. This gives us control to compare against our subsequent measurements. Then we expose the target to our ring laser in controlled cycles, where we'll also be varying several parameters such as the ring laser power, exposure time, and the ring laser frequency. Finally, we'll perform control experiments, running the entire procedure with the ring laser turned off to isolate any effects from our measurement process or environment, and reversing the ring laser to test for any directional dependencies. All right, now I hand over to my colleague Vysakh to explain an experimental verification method involving stead simulated emission.
Hello. So I will be discussing about the second experimental part involved, which is mainly the experiment involving STED microscope. So this is the same setup as Dominic said. Dominic, can you go to the next slide? So this is the experimental setup. So we mainly use a target source, which is stained with a fluorescent dye. We perform the experiment mainly using two lasers. First one is a normal diode laser. We pump the laser beam to the target from the left side, which is also known as the forward beam. This excites the electron of the particular target source from the ground state to the excited state. So as a result, the population in the excited state increases, which results in a population inversion. This causes a radiation. Now, simultaneously, we will pump using an STED laser. The characteristic of an STD laser is that it causes radiation, but no fluorescence will occur. So as a result, instead of observing a large bright image, we will just observe an excited spot on the photodetector, which is further studied by the oscilloscope to measure a delay between these two beams to confirm that there is an existence of both forward and backward beam. Can you go to the next slide? So these are the methods involved. So first we use a fluorescent dye. This is mounted on a microscope. Then we pump the diode laser, which causes the excitation. At the same time, we will pump using an STD laser. This causes the de-excitation, but with lesser fluorescence. And finally, we obtain an image that is an excited spot on the photodetector, which is detected by an oscilloscope. So now, as we can see here, there's a graph. The blue dotted line is what we would expect when we do this experiment. But due to the presence of this STD laser, what we obtain is the red curve. So this gives us an idea about the existence of both forward and backward beam within the same setup. So that's it about the experimental part. Thank you. And if there are any questions, please feel free to ask.
Thank you. Yeah, I think we will proceed with the last presentation, and then there will be time for questions for all of the presentations. So who is going to present now? That's the last presentation now, right? Paweł, you are unmuted, but we cannot hear you. Because you were saying something. Wasn't that-
One more person, but I don't see him. So, I think we can finish.
Okay. So then that was the last presentation. And are there any questions to this presentation, previous presentations?
And by the way, can you hear me now?
Yes.
Okay,
Now we
so
can hear
it
you.
seems there were some technical issues with my microphone. Sorry for this.
Yeah, we didn't hear you at all, actually. Yeah. Any questions? Yeah, okay. If there are no questions, then I will ask a question to this experimental part, because it's kind of interesting. Could you tell a bit more about this this setup? About the ring lasers. I'm not sure if I got what the ring laser is exactly. This presentation.
So Dominic, are you going to answer?
Hi, yeah. So in general, a ring laser is really a laser in. Actually, let me share my screen. I have a slide. with this diagram. Yeah. So a ring laser is mainly composed of two beams of light, and these beams of light have the same polarization. And they'll be traveling in opposite directions in a closed loop. So you can see this like sort of triangular formation. And so this triangular formation of the light is what creates this closed loop. So that's what the ring laser is.
Okay, thank you very much. Any more questions? If there are no questions, I think we can conclude. Aritra, are you with us?
Yeah, I'm there.
Would you like to conclude?
Yeah, sure. So thank you again for all the presentations through the full QIntern workshop. So we had 12 presentations out of 18 total groups. Out of that, already 4 of them were not part of the workshop. And I think it was like a really good spectrum of different projects, right from experiments to theory to fun projects. Yeah, and I think the rest of the procedure is already there listed on Discord regarding the videos and how the gradings will be done and how the certificates will be distributed. So yeah, that's all. Have a nice day, everyone, and thanks for joining.
Thank you.
Thank you very much.